something fun. And I needed this because I wanted to have an animation and also be able to play with it with keyboard. After spending hours and hours trying different things, I realized that the best way to do this is PyGame. So look at this. Do you see how smooth this animation is? Yes. And I can play with it. So I actually put it into this gaming keyboard, ASDW. So if I press W, it will start from the top and it will drop like this. Okay. If I press S, it will stop from the bottom and will not move. If I press D, it will get a kick to the right. Okay. Let me put back it on and kick to the left. Let's have another kick. Let's have multiple kicks. That's a lot of fun. Okay.
Can we also add the lines to show their path trajectory?
Yes, we can, but we will not. Yes, we can. Yes. Very good question. Let's look at the code that generates this, so you will get your answer. So to get this, you have a calculation part. Calculation part is the same as previously. Like it's double pendulum that we already did. Do you remember that? So you have some calculation parts. Inside the calculation part, let me put it here and it will just run. So it will keep you busy. Or should I just do this so that you are not distracted? Yes. So the calculation part, you turn it into a function. So update variables function. So what goes in are the angles and the angular velocities and how many times you are going to run forward the calculation, how many dt forward you are going to go, and then the rest is, do you know how to get rid of this? No? Okay. Not the copilot, but the explanation. You know, when I go here. Okay. Okay. For now, let's see if we can handle it without it. Okay. So do you remember this whole code that we did before? You just basically run this calculation nt times. So basically it returns the new theta 1, theta 2, omega 1, omega 2 after nt times delta t time delta t time later. Good? Then the animation part. You start by importing this PyGame. And inside PyGame, you basically have some initializations. So the screen has some width and height. And you actually define some colors if you want. Black, white, red, blue. I don't know what this does. Just live with it. The main part is here, the drawing. So you get the input of screen x1, y1, x2, and y2. And it basically draws some lines that goes from the middle of the screen, width divided by 2, height divided by 2. Are you following? Yes? To middle plus x1, middle minus y1. Why minus y1? Because the screen calculates it from the bottom to the top, okay, the pixels. So we are flipping it top to bottom. Does it make sense? Yes? So you draw the lines and you draw the balls. And then there is this part where you can basically, if Q is pressed, then it does this. So it quits. If S is pressed, remember S was putting it down like this. If S is pressed, then theta 1, theta 2, omega 1, omega 2 are all 0. If W is pressed, it becomes upwards, right? So you have pi, but then pi plus some random number, a bit of a randomness, so that it doesn't just stay like that. It has just a bit of randomness so that it falls down. Does it make sense? Yes? Good. And finally, to answer your question, when I press D, omega 2 gets a kick of +1. And when I press A, omega 2 gets a kick of -1. So it goes like this or goes like that. Are you happy? Yes? Any clarification needed here? No. Good. So we will use it to figure out Schrödinger's equation, of course. But first you need to know what it is all about. So now that we had a bit of fun, now there's a long part of a lecture time, okay? But yeah, we will get back to computation at some point. So the chapter is called Schrödinger. And we will talk about almost everything except his cat, maybe. But actually, we will talk about his cat as well, in a sense. So, I will start with 2 experiments, okay? Some of you have already seen this in MSN 517. But yes, let's remind ourselves what those experiments are. So the first experiment is, the first title related to experiments is ultraviolet catastrophe. And don't worry, I will be quick, because you have listened to it a million times. Not you, but ask me questions if it's not clear. So if you take the light coming from the sun and put it in a spectrum, so here is a spectrum. Let's duplicate this. Classical theory. So what is this? This is frequency. This is energy density per frequency. Okay? There is some light coming from the sun, okay? And you basically put them into their frequencies. So light is yellow, right? So mainly the frequency, the maximum amount of frequencies that we are receiving are in the yellow part. Okay? So if you draw it, it looks like this. Okay? If you look at the energies, let me draw the wrong one first, because it's easier to draw the wrong one. The wrong one is going like this. It's a quadratic equation. So classical physics, this is classical, predicts that df over du over df should be proportional to f squared, but the experiments are like this. Are you happy with this? No? If this doesn't make sense at all?
No, it doesn't match
Hmm?
Because of it doesn't match, I don't like the result.
Yes. So, very good. People also didn't like the result. So, it was first matched by Planck in 1900s. So Planck came out with a formula for it that fits it, okay, in the early 1900s. But then there is this couple of months in between where probably he couldn't sleep because he just had the formula. He didn't have the physical explanation why that formula should work, okay? But at some point, he realized that the formula works only if you assume that energy is a quantized multiple of frequency. Okay, let me explain what it means. So we have seen classical harmonic oscillator, right? Classical harmonic oscillator looks like this. So if I started with some x0, then the energy of the system, the total energy is k x0 squared over 2, right? So can I set x0 to anything I want? Classically? Yes. So classically, the energy goes between 0 and infinity, and it's continuous. Okay? As much energy as you want, and you can put 0 energy as well. But quantum mechanically, quantum harmonic oscillator says that, by the way, you can see energy can be anything, has nothing to do with frequency. The frequency is square root k over m, and you don't see any square root k over m here. Doesn't matter whether your spring is stiff or soft. It doesn't matter whether your mass is massive or not. As much energy as you want, you can put in an oscillator. Quantum mechanically, the story is different. Omega is still square root k over m, but energy cannot be 0. Okay? Energy can be only h bar times omega, 2 h bar times omega, 3 h bar times omega, etc. Are you with me? Yes? Okay. So what? I had a point here and I forgot what was the point. H bar. What is H bar? H bar is a constant. It's a constant that is around 10 to the minus 34 joule times second. Okay? So far, any questions? You have seen this in high school physics. Is that right? No? Well, we will come back to the explanation. So far, you just have, so this historically, it's first of all Planck's formula, then Planck's formula for ultraviolet catastrophe that fixes it, then Planck's formula that fixes that formula, then it's Schrödinger's equation that fixes Planck's formula. So you see the reasoning here, you get some experiment, you put a mathematical function on top of it. To explain mathematical function, you say that energy is quantized. To explain the energy is quantized, you have to go to Schrödinger's equation. And each time you do this jump, it gets more and more ridiculous in terms of classical intuition. You see, we already have this ridiculousness here. Why I can't put just any energy? I would just go and just stop it, right? It tells you that you cannot stop an oscillator. So, and if you have an oscillator, it will oscillate, definitely. You see? Good. That's the first experiment. The second experiment is the Stern-Gerlach experiment. So this was the problems of 1900s, right? Actually, I mean, the experiment itself starts early in 19th century, I guess. This is from 1921. Can you check? So, like 4 years before Schrödinger's equation. Okay, so Schrödinger's equation is not there. Here's the expression. Here's the experiment. You take some silver atoms. Okay, you send them through a non-uniform magnetic field. Okay, non-uniform magnetic field. And what you expect is that depending on its angular momentum, it will have magnetic moment. Okay? If you take something that spins, this whole thing will become more and more ridiculous. But so far, let's make it less ridiculous. Let's say you have a charge and it spins. It can spin this way, it can spin that way, it can spin this way. It doesn't matter, right? So, and I'm just telling you that if it spins up, then under non-uniform magnetic field, it wants to go up. If it spins down, then in non-uniform magnetic field, it goes to go down. Okay? If it spins sideways, okay, it will go up just that amount. Like if it comes like this, it will not go up or down. So let me repeat. I'm applying magnetic field in z direction, non-uniform magnetic field. If it comes like this, nothing happens. Comes like this, goes a bit up. Comes like this, goes really high. Comes like this, goes really down. Good? So what you expect classically is a distribution here, right? Some go up, some go down, because you don't arrange it beforehand, okay? But what comes out is just two sharp peaks, okay? Weird. Just two sharp peaks. So it tells you that angular momentum is quantized, okay? And it was expected. There are lots of things about it that was not expected, but it did fit to an early version of quantum theory that is nowadays called old quantum theory, that is due to Bohr. Do you remember Bohr atomic model? So it would fit in a way, it would fit Bohr's predictions, but not. There are lots of things that were like ridiculous as well. But it gets more ridiculous. Okay? Let's say I accept it. Let's say I accept Bohr's ideas or whatnot about this quantization. What if I get up and down like that, but now I want to measure it in x direction? What will happen? Okay? Do you have any ideas? So this time I have filtered out. So I sent an object that I didn't know what it was. I measured it in z direction, and it came out as up and down. Let's say we are okay living with this. What you expect is that since this is aligned in z direction, what you expect that if you measure it in x, you should get 0. Do you agree with this? Let me explain. If it comes up, okay, it's quantized, whatnot, so it's definitely up, it's filtered. Now I'm looking at it sideways. What I expect classically is nothing because it's perpendicular, right? It comes exactly perpendicular. what comes out? Up x, down x. It seems like your experiment is changing the nature of reality. When you measure it, the system changes. And at first, people thought that it has to do something with the interaction. So we are like bothering the system while we are measuring it. That's why it's coming out like that. So far, so good? The thing is that, okay, let's accept also this one. Let's accept this one. Something is hidden there, whatnot. Do we agree that before entering X measurement, it was at least up? Right? Let's at least expect this one. Okay, we accepted all this. Let's at least expect that if I do Z measurement here, let's at least weight it to be 100% up Z. Right? Because it entered up in Z direction. Okay, X did something to it, but in I measure in Z direction again. Well, no. Up Z, down Z. 50% this way, 50% that way. Also, this one is 50%, 50%. And this one is 50%, 50%. Do you see the levels of weirdness involved here? Yes? So it seems like measurement is a weird thing and it changes reality, but we will understand, hopefully, that it is not due to the interaction, it is due to the very nature of reality. Okay? 2 experiments. Now let's talk about, so years have passed, everything is settled, we now have an equation for everything that explains everything. So to understand that equation, you need to know what is a wave function. We will come to the code. Don't worry. It will take some time. What is classical? If you have a particle, how do you describe its state classically? You say that it has this position and that momentum, right? If you know what is the position and the momentum of a particle, you can predict its future. And nature is deterministic in that way, right? Well, once you come to the fully fledged quantum theory, in the modern quantum theory, this is replaced completely by something called the wave function. So instead of position and momentum of the particle, everything about the particle is described inside this wave function. Did you follow this so far?
Yes.
Very good. And we will think of this function, maybe it's early to say this, but let me remind you, if you have watched the prerequisite videos, we think of these functions as infinite dimensional vectors. Right? Just imagine a function. You can discretize it. Then you represent function with a bunch of numbers, right? Just like we do in the computer, don't we? Now, as many grids as you are using, your function becomes that much dimensional vector. What is the vector's value in the first place? It's this one. Second place, it's that one. Do you understand? There you go. Now we are ready for the Schrödinger's equation. Do you have any questions so far? Did you follow so far? Yes. Especially for those who, those people who are seeing this for the first time, Schrödinger equation. Schrödinger equation looks like this. It's the weirdest equation ever. Why? Because it has I in it. Do you know any other equation that has I in it in the classical world? I mean, up to Schrödinger's equation, we didn't have any I in our equations. But it turns out, I mean, it looks just like a normal diffusion equation because, look, you have so far, doesn't it look like a diffusion equation? Yes? Except for this. Yes. And it has also this source part, yes, the potential part, which is also not so new if you think of diffusion equation. You also have source terms in the diffusion. What is different is I, and I forgot to mention, but this is also a good point to mention it. Psi of xt is a complex valued function. That way, you can also write this equation down without I. It is possible. How can you do that? How can you write Schrödinger's equation without?
As a coupled system of PDEs.
As a coupled system of the real part of the wave function and the imaginary part of the wave function. Do you understand this part? Yes? So it is possible to get rid of I, but then there is Occam's razor, right? The simplest explanation. So it's much simpler with I in it and having one equation than having two functions that are coupled, that we know is two sides of the same coin. Why bother stripping them apart, right? Anyways. So, Schrödinger equation would take you from phi xt to Schrödinger's equation would take you from, actually I should really write SCH, right? That's one letter in principle. Psi x t plus delta t, no problem. It would just take you safely from time t to t plus delta t. And in that sense, quantum mechanics and Schrödinger's equation, in that sense, is deterministic. Okay? Give me wave function now. I will tell you wave function after 1 hour using Schrödinger's equation. So far, how are we doing? Was it just 1 page or 2 pages? Where's the other page? Anyways. Okay, it's at the back. So we are done with 2 pages. 2 pages to go. Do you have any questions? Please ask questions if you have any.
Hocam Stein-Geber experiment. Is this how the quantum computers work?
It makes part of it. Okay. It's definitely not related. Okay. Or shorter answer, I don't know. But that would be not accurate. So I do know a little bit. Measurement and operators. So Schrödinger's equation fixes Planck's problem. If you take a harmonic oscillator, okay, harmonic oscillator is just Vx equals kx squared over 2, right? If you solve that equation you just get E equals to, you just get the discrete energies, okay? Only once you get from the Schrodinger's equation, let me just tell you, you get not E equals to n h bar omega, you get just a little bit different, just a little bit different. E equals to n plus 1/2 h bar omega. That's what you get. Close enough, right? But what about the problem with the measurement, with the Stirn-Gerlach stuff? Do you remember? So to understand that one, we should understand what measurement is in the context of quantum mechanics. So as I said, state of a system is represented by a function, right? State of the system is the function psi x, and we think of it as a vector phi. So far so good? Now measurement in quantum mechanics, so state is represented with functions which are really vectors, yes? Measurement is represented by operators which are really matrices. Let me give you an example. What is momentum measurement correspond to? Momentum measurement corresponds to
minus IH bar gradient.
exactly. Should I go with this? Is that okay if I do this one?
Yeah.
Yes? So why do you know this? You took quantum mechanics course?
Yeah, I took German.
Do you see this? Very weird. And I will not explain this to you. Why this is like that, I will not explain it to you. You just like if you ask why Schrödinger equation is like that, I didn't explain you that. For this one, please take it for granted. But I did explain to you that taking a derivative of a function corresponds to multiplying it with a vector, with a matrix. Do you remember that?
Yeah.
So this derivative does really correspond to a matrix that if you are using 3-point stencil, okay, then it looks like this. H bar 2i delta x, then zeros here, minus h bar 2i delta x, zeros here, and it goes on like that. So you see, this course is not unrelated chapters. It's quite related with the previous one, right? Operators correspond to matrices. Yes? Yes hocam, devam et. Continue. Let me give you another famous, important measurement. Let's say you want to measure kinetic energy of the system. What is the corresponding operator? Now, what is momentum? It's P, right?
Yeah.
What is kinetic energy?
P squared over 2m.
P squared over 2m. So let's do P squared over 2m here. So 1 over 2m times P squared. What do you get? H minus h bar squared. Exactly. Do you see it? So kinetic energy is also represented with an operator which is really a matrix. Okay. Let me just write it like this. H bar squared over 2m delta x squared. Okay. And then inside you have, let me think, minus 2, 1, 0, dot, 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 minus 2, 1, 1, 0, 1, minus 2, 1, dot, dot, dot. This is, of course, to the first order, to the 3-point stencil, but it is a matrix. Good? Who has a question? Any questions? Who can summarize what I just said? Can you summarize? You seem to be following it.
I follow it, but I have to write so many. But
Yes, just try.
we do that, explain both momentum and kinetic energy part of the matrices inside using the equations and take their orders, the first order. If I understand.
Yes, so measuring kinetic energy has something to do with taking the second order derivative of the wave function, and it is really a matrix. Okay. Now comes the part that is related to Stern-Gerlach. How your measurement actually changes the system, right? And it has nothing to do with interaction. We call it wave function collapse. Okay. To understand wave function collapse, let me remind you that operators, so I will take an operator Q and I will show it with this hat. Whenever I put a hat, it's an operator, but I sometimes forget. That operator was really a matrix, right? So I showed matrices with this. Now, not every matrix, but I didn't tell you, but all the measurable stuff are Hermitian matrices. All the measurable stuff, like you can measure position, right? Yes? Then the corresponding operator should be Hermitian. You can measure momentum, right? The corresponding operator should be Hermitian. Is it Hermitian? Let's check.
Yes.
Yes, it is, because look at here. If you take the transpose and conjugate, it will be the same matrix. Look at this one. Take the transpose and conjugate, and it will be the same. So it has that symmetry, right? So what do we know about Hermitian matrices? They have positive, not positive, real eigenvalues and orthonormal eigenvectors. So this Q operator will have eigenvalues and eigenvectors, right? So this Q will give you Q1, Q2, Q3, and they have nothing on their top, hat or bar or double bar, so they are numbers, okay? They are actually outcomes of that experiment. So you measured energy, you can get Q1, Q2, I mean, when you do energy, you can get E1, E2, E3, and each one will have its own eigenvector. So it will have, it will have Q1 vector, Q2 vector, Q3 vector. So far, so good? Very good. Almost there. So what I'm trying to say is Q matrix times Qn vector is equal to Qn number times Qn vector. It's an eigenvalue equation. Now, since Qn's are producing a complete basis, they are producing orthonormal basis, right? Can you write your wave function, which was also a vector, right? Can you write it down as Cn times Qn?
Yeah.
You can do this for any function. Are you still with me? Yes? We are almost there. How do you find Cn?
Just take the product from left.
Yes. Can I do this?
Yeah.
Do you remember this? We would have eigenvectors, okay, and to find, we did it with inverse Fourier transform, if you remember. We had Fourier transform vectors, And then if we took their conjugates and multiplied the function, it would give us the coefficients. Do you remember that? Here is the measurement phenomena explained once you have all this picture. Let's say you have a state phi, and you are going to do a measurement q. Okay? Quantum mechanics tells you that with C1 squared probability, you are going to get Q1. With C2 squared probability, you are going to get Q2, ... Okay? And that's where God throws dice. Okay? That's where the non-determinism of quantum mechanics lies. So far, everything was deterministic. I give you phi, you give me phi t plus delta t, right? But when you do measurement, you are asking a question that wave function doesn't want to answer. Okay? Because wave function is, let's say you are going to measure energy. And wave function is composed of different energy eigenstates. So it's like this much energy. It's in the state of the Schrödinger's cat. It's both dead and alive at that moment. Okay? Superposition of two, E1 and E3 and E5 can be anything. Then you ask, what's your energy? Since you want a definite answer, it has to fit to your question. Okay? And what happens is that it collapses into that eigenstate. So once you get your answer E1, then your wave function is no longer phi, but it suddenly, abruptly collapses to the eigenstate. So that explains, well, if you take it as an explanation, that at least describes mathematically what's going on with Stern-Gerlach experiment. You send a something that is measured in x before, and you know that it's x like this, right? But when you ask, what is your z, it looks at that and says that, okay, I can construct this by using half of z like this and half of z like this, okay? So my answer is this. I'm half that. So half of the time it will be up z, half of the time it will be down z. But once it's up z, if you measure it again, it will be up z again. That's why it has to collapse also. Why it has to collapse? Because, let me tell you why it has to collapse. Let's say you measured energy, total energy, and it came out as E3. Okay? If it still stays in somewhere around phi, like phi plus delta phi, phi plus epsilon. It's affected by it very little bit. Okay? If you do another measurement, then energy could be E2. And that doesn't make sense. Because I just measured energy, and I haven't spent any more time for it to change, and I measure again. If you want measurement to make sense, the consecutive measurements should be 100% the same. Does it make sense? I just measured your position. You are here. Then I measure your position. You are there. Can it happen? Quantum mechanics is not that ridiculous. That's the point. But to account for that much of non-locality problems, to account for that, once I measure your position, your wave function has to collapse into that eigenstate of that measurement, so that if I measure it again, it has to give me the same answer. Does it make sense? Yes.
Why doesn't classical systems collapse?
Okay. Why doesn't classical systems act weirdly in general? Because they are big. Okay, all these things get important when you are at nanoscale. Okay, I mean, let me talk about it more after the break. Okay, let's stop here.